All right, so we're in chapter 5 now, and chapter 5 for us is going to be one of the shortest chapters for what we're covering. Might actually be the shortest. We're only going to be looking at section 5.1, and of that section, we're only going to be looking at about half of that material. Section 5.1 is split up into 4 subsections, and we're looking at the first 2 of those, both of which deal with what we call spring mass systems. The physical concept that we're looking at here should be kind of familiar because you explore this from a different perspective, slightly different perspective in Calculus 2. When doing work problems, you talk about things like Hooke's law, which we're using here. If you've had physics or engineering classes, this is something you most likely would have encountered also. Because this is an applications section, we're going to be dealing with a few things like units of measure, concepts like mass and weight and stuff like that. And I'm going to be kind of making the assumption that you're familiar with some of those basic concepts. So if you're forgetting, for example, what's the difference between mass and weight, what are the units of measure for these things in imperial or metric units, you might want to look some of that stuff up just to get a refresher. But anyways, moving on. Section 5.1.1, the first section that we're looking at, deals with, like we said, spring mass systems and a specific version of that we call free undamped motion. So the idea here is that we're looking at a spring suspended from some kind of rigid support, like a ceiling, for example, and then a mass being attached to the other end of that spring, some kind of weight. I have some pictures down here sort of illustrating this, but we'll get to this diagram in a bit. There's 2 physical laws that we are going to be using to do the work that we need to do here. First is what's called Hooke's law. So again, this is something you've probably seen before, but we'll kind of give you the recap on it. So if you take a spring, like what we just saw in that diagram, attach a mass to the end of it, the mass should elongate that spring. And Hooke's law is a description of the force exerted by the spring in a specific way. So basically what Hooke's law says is if again, let's use this diagram. If this mass elongates this spring, then the spring is going to exert what's called a restoring force. In fact, if you pull the mass down, the object down even further, then it would go on its own and then release it. The spring is going to pull that up. So you have this force that's entirely due to the spring, which we call a restoring force, and it's pulling the mass toward that rigid support if the mass is down here, or if the spring has been compressed, the spring is going to push the mass away from the rigid support. So it kind of depends on the position of that mass at whatever time you're looking at. So Hooke's law is a description of that restorative or restoring force, which we're going to call F. Okay? Now, I'm going to go back to using this diagram again here. So let's suppose, for example, that the spring that we are using in this system has a length L, and then once the mass is attached to that spring, it's going to pull it down by an additional S units. Okay, so S can be thought of as the amount of elongation of that spring due to that mass hanging on it. Okay, that's what we're going to be calling S. So Hooke's law says that restorative force, the force that's due to the spring, is directly proportional to that length S, the amount by which the spring has been elongated by that mass or by whatever force is pulling down on it. Put in mathematical terms, to say that is to say that F is equal to some constant times S. And we express that this way. F is equal to negative Ks, where K is assumed to be positive, meaning negative K is negative. The purpose of that negative there has to do with how we impose a coordinate system on this thing. So we're going to show this in a little bit, but when we have these spring mass systems, we're thinking of a single axis, a vertical axis, where the string becoming longer we'll pull that mass in the downward direction, and we're going to think of down as positive. So the axis is going to be oriented so that the downward pointing part of that axis is the positive axis. Upward will be negative, and we're going to talk in a moment about the equilibrium position. There's a place here where we're going to think of that as the 0 on that axis. Okay, but because the force is going to be acting in the opposite direction as gravity, and gravity is pulling downward, the positive direction, we're going to be thinking of Hooke's law, the constant here, or the force, as a negative force. It's pulling in the opposite direction, which is why that minus is there. Okay, the K that's showing up in this equation is what we call the spring constant for that system. All right, so Hooke's law is we can summarize basically by this: the restoring force of the spring is equal to negative the spring constant times the displacement of the spring. We can think of that as displacement. Okay, next up, another important physical law that we've already discussed, and you're bound to have used this multiple times in previous classes, Newton's second law of motion, F equals ma. Okay, so again, what this means is this: if you have a mass m, and it's in motion with some acceleration a, which can be 0, then the net force F acting on the mass, the sum of all forces acting on that mass, is going to equal ma. Okay. Now that applies here because there's forces at play and there's motion happening. So we can apply Newton's second law to this spring mass system. So again, let's suppose that our mass m is attached to that spring, and like we said before, we're going to assume that the spring has a length of L, and the mass when attached to the spring elongates the spring by an additional s units. Okay, so that the total length from the rigid support to the mass itself, when it's just suspended there, is L plus s. Okay. Now, the equilibrium position is what we call the position on that vertical axis that we're going to orient this thing on. It's the position where the mass is this right here. So let me say that a little bit differently. When the mass is attached to the spring and the spring is left to hang, and assuming the mass is not moving up and down at this point, wherever it's ended up, L plus S, we call that the equilibrium position. And we're going to orient our axis, our x-axis, so that the equilibrium position is at 0. And then anything above that will be considered a negative position. Anything below that will be considered a positive position. Okay? Now, because the object here, the mass that's suspended by the spring, is not moving, then all of the forces in this system are balanced, meaning the sum of those forces will be 0. But what forces are we considering here? We're only going to consider 2 forces acting on this spring, or on this object. There's the restoring force of the spring, which acts upward, and we consider that the negative direction. Then there's the downward force of the spring due to gravity, the weight of this object, we consider that positive. And so the sum of those 2 forces should equal 0. Well, we know, again, from physics, we've used this before, that the force due to gravity on a mass m is equal to mg. That we also think of that force as weight. Weight is a force. So we can also say W, the weight, equals mg, mass times the gravitational constant, or the acceleration due to gravity, not the gravitational constant. So that is a positive force acting in the positive direction, and according to Hooke's law, the restoring force of the spring is negative Ks. So the sum of those 2 things, which now actually looks like a difference because one of them was negative, is equal to 0. Okay, and that's what we're understanding from this equilibrium position right here. Okay, so that's important. We're going to need that. Moving on to the next page here. Here you can see the how the position of our mass spring system works within our coordinate system. At equilibrium, when the object is just suspended there with no motion, we consider that x equals 0. If the spring is compressed, pushed upward above the equilibrium position, we're going to call those positions negative. And then anything that requires the string to be stretched, pulling the mass downward will be giving us a positive position for that object. Okay. Now, if we pull this mass down or lift it up so that it either elongates or compresses that spring and then release it, maybe with some initial velocity or maybe from rest, or if we leave the object at the equilibrium position and apply a force that creates an initial velocity either downward or upward, what's going to happen is the spring is going to oscillate. The object is going to be moving up and down as the force due to gravity and the spring kind of oppose each other and cause that oscillatory motion. We call that free motion when that's occurring. Okay, and what our goal is we want to come up with an equation here that describes the position of that object at a given time t once that's happened, once this thing has entered oscillatory motion. We're going to think of time t equals 0 as corresponding to the moment that mass was released and this motion was begun. Okay, so in order to do this, we're going to use, first of all, that, again, we're talking about a position function, x of t, and we know from calculus 1 that the acceleration of this object is the second derivative of that position function. We need that because, again, Newton's second law, F equals ma, has us using acceleration. So according to Newton's second law, the net force acting on this object is ma, the mass of the object, times the acceleration, which is the second derivative of x with respect to t. But another way of thinking of net force is just the sum of all forces acting on that object. And so again, let's think of what that would look like. The force due to gravity, again, is mg. What can we say about Hooke's law, how that impacts the position or the force? That force is changing because remember, the force due to that spring is directly proportional to how much that string has been elongated or compressed. And you'll see here we have negative kx plus s. Well, negative ks, this thing right here, where we were looking at Hooke's law, is using s to mean the amount by which the spring has been extended or compressed. Okay, but now the way we're thinking of s is that s is just the elongation of the spring when the object is in equilibrium position. If we also, let's just say for example, pull the mass down by an additional length of x, then the total elongation of that spring is x plus s. Okay, the amount that we've pulled it down from equilibrium, which already took it down in s units. So that's why we're seeing x plus s here. Hooke's law would give us this. Now, if we distributed the negative k in here to get this, notice we have mg here, negative ks here. We've already shown that this is equal to 0 right here. So this term zeroes out and simplifies by a great deal. It becomes negative kx. Okay? So I have m times the second derivative of x with respect to t is equal to negative kx. Now, if I divide everything in the system by m and then move this term over to the left-hand side, it becomes this. Second derivative of x with respect to t is plus k over m. Remember, both k and m are constants here, so this is a constant, times x equals 0. We have a second-order linear homogeneous differential equation with constant coefficients, which we have dealt a lot with up until this point. To simplify the notation a bit, we're going to take this constant k over m and give it a new name. I'm going to define that to be equal to omega squared. Now, the reason it's equal to something squared and not just omega is because that's going to make the next step or two look nicer. Okay, if I didn't set this equal to omega squared, if I just called it omega, then the equation that we're going to end up with is going to have radicals in it, which just in our stingy opinion does not look very nice. So we're going to use this. It's okay to do this because both k and m by definition have to be positive. So squaring this, which should only produce a positive number, doesn't create any contradictions here. So with that, this equation becomes the simpler looking second derivative of x plus omega squared x equals 0. And this is what we think of as what we call the equation for simple harmonic motion, or again, free undamped motion. This equation characterizes that type of oscillatory motion, which goes by either of these names. Now, to solve this, we would find the auxiliary equation, which would just be m squared plus omega squared equals 0, which is very easy to solve. Its solutions would be plus or minus omega I. So we have complex conjugate solutions for this homogeneous linear DE with constant coefficients. That, from our work back in chapter 4, we know that means that the solution is x equals C1 cosine of omega t plus C2 sine of omega t. And here's why we wanted this to be omega squared, so that this would come out to omega instead of root omega, making that look a little bit nicer. Okay, now we can actually do better than that, because in these problems where we're looking at these spring mass systems, they tend to be IVPs, because we have an initial position usually that we know, x naught, and that's wherever we're releasing the object from according to our vertical coordinate axis. And then we could also talk about the initial velocity of that object. If you release the object from rest, for example, the initial velocity would be 0. But if you, say, apply a downward force, giving it a positive initial velocity, then x1 would be equal to that positive initial velocity. Or if you propel the object upwards, giving it an upward velocity, we would call that negative velocity, and that would correspond to x1 as well. So we have these initial conditions. X of 0 equals x naught, and because x is a position function, its derivative is a velocity function, so x prime of 0 equals that initial velocity x1. That gives us initial conditions allowing us to solve for C1 and C2 here. Okay, so once we have evaluated those and found the actual values for these parameters, C1 and C2, and plugged them in, what we have is what's called an equation of motion. For some reason, motion was not bolded here. It was supposed to be. Equation of motion should all be bold. That's what we're calling this equation for that given system. Okay, now this function, when it has a common argument in the cosine and the sine like this, omega t and omega t, we can show, which we will in a little bit, that this can be written as a sinusoidal function, which means it can be written as just a sine function with some alterations made. Because of that, everything that you learn about sinusoidal functions back in trigonometry, all the characteristics of those functions can be determined for an equation like this. For example, this function has a period. Its period would be 2 pi over omega seconds per cycle. So that means that this quantity, 2 pi over omega, is going to tell you the amount of time that passes for the object to complete one full cycle, meaning go completely up, down, and then back to its original position. That's what a cycle would look like. We also know that frequency is defined to be the reciprocal of the period. So I could talk about the frequency of this system as well. The frequency would be omega over 2 pi cycles per second. Okay? And then in addition to that, one thing that we know about sinusoidal functions, sine waves, is that they have periodically occurring absolute maximum and minimum values. So the positions that those correspond to are what we call the extreme displacement of the mass. And again, what that basically means is how high the mass will go and how low the mass will go, the absolute highest and lowest positions of that mass as this spring is oscillating. Finally, that number omega that we defined in our on the previous page, which would be equal to the square root of k over m, is what we call the circular frequency of the system. So there's a lot of terminology attached to these quantities. Okay, I want to look at an example really quick. So a mass weighing 24 pounds attached to the end of a spring stretches it 4 inches. Initially, the mass is released from rest from a point 3 inches above the equilibrium position. Find the equation of motion. Okay, you could draw a diagram for this. You actually don't really need to if you know what to do with these quantities. So first thing I want to point out, pounds. We're using pounds here. 24 pounds is not a measure of mass. It's pounds are a unit of weight. Okay, and we know this is directly from Newton's second law. Weight, which is a force, is equal to the mass of an object times the acceleration due to gravity, which is g. Okay, this implies that the mass of this object is equal to the weight of the object over g. Now, the weight of this object, we're told, is 24 pounds. G is not 9.8. Remember, that's in metric units. We're using imperial units, pounds, inches, feet, that kind of stuff. The acceleration due to gravity in imperial is 32 feet per second squared. So I'm going to say 32 here, which simplifies to 3/4. And the unit of mass, you may not actually know this, but the unit of mass in imperial units is slugs. It may not be that familiar. You may be used to thinking of mass in kilograms or grams because that's metric. You're going to use metric more often in the sciences. But in imperial units, mass is measured in slugs. Okay, so with that, what else can we say? Well, the next thing that we're going to need is S. Remember, S is the amount by which our... let me go back to that diagram if I could find it. S... hold on one second.